Hey everybody, it's Ripley back again. We're talking about the fundamental theorem of line integrals today, this is a super fun section. I enjoy this. We're going to do some puzzling. But first, before we get crazy, let's talk about what a conservative, we need a little vocab. This is going to be a vocab heavy section, okay? We're going to talk about a conservative vector field, all right? What is a conservative vector field? Well, if you recall from a couple sections ago, a conservative vector field is a vector field we'll call boldface F such that F is equal to the gradient of F. In other words, there exists, let's say, there exists an F of xy or xyz or whatever such that when I take the gradient of that F, I get my vector field F. Okay, that's a conservative vector field. Now, in this section, we're going to define, we're going to come up with all kinds of ways to prove that a function, or that a vector field is actually a gradient of a function. All right, but think about what that means here for just a sec, because this idea is really important, and it dovetails really nicely with the fundamental theorem of line integrals. Okay, so here we go. This is the fundamental theorem of line integrals. All right. So what it says, I'm gonna write the whole thing out, but it kind of sucks, but that's okay. All right. It says let C be C. In other words, we've talked about C, right? We got a smooth curve. We've got a smooth curve. Given by some vector function. By vector r of t between values, we got t between a and b. Okay, kind of standard issue. All right, and f be a diffable function of two or more variables. Of two, I hate writing these out for you guys, or more, but I'm sorry, variables, just like I said up here, whoop, this guy up here, who with gradient vector delta f continuous on C. In other words, what that means is my partial derivatives exist. All right, my first order partial derivative exists. Otherwise, I can't have a gradient vector that's continuous. So that's just another way. All right, this implies, now here's the punchline. You ready? This implies that the line integral across C of gradient f dot dr. Now remember, gradient f is just another way of saying this. Okay, dr is equal to little f of r of b minus, oops, little f of r of a. Now, let's be clear. Remember, this is the gradient of something, which implies that this is still a vector field, right? This is still a vector value function. Think about that, of c, f, dr, right? And what we're saying here is if this f is actually a gradient, right? If it comes from a function where we took the gradient and now we've got this vector field, then we're going to have f of r, well, I'm sorry, I'm not going to rewrite that. You guys will punch me in the head. Well, don't punch me in the head. That would get you in trouble, and it would hurt. That will give you this guy as well. All right, so that is the fundamental theorem of line integrals. Now I'm going to prove it for you, but then let's talk about some ramifications of it, because that's kind of heavy. All right, so let's do. Now, one point I want to make before I do the proof of this, because the proof is pretty interesting, it's kind of fun, is if you notice, by virtue of the fundamental theorem of line integrals, we are given that this line integral contains a conservative vector field, and that's really important. To have a conservative vector field, and that's why I went into what a conservative vector field was first before I got started. Okay, so here I'm gonna prove this for you really quickly because it's actually super easy to do. All right, I'm gonna take the line integral of gradient of f of dr. And I'm going to rewrite it. Now, remember, this is still just a line integral, so I can write it in whatever form I want. I can do like an f dr like I did before. Remember, I can also do f dotted with t, if you remember that guy with the ds. Or I can write this, excuse me, as the integral from a to b. This is from last section, of gradient of f of r of t dotted with r primed of t dt. You remember that from last section? That was we liked that one. That was a pretty useful one, if you recall. Excuse me. Now, remember that the gradient is just partial derivatives, right? So I can rewrite this. I can rewrite this as the partial of f, partial of x, plus the partial of f with respect, I didn't mean partial of x, I mean with respect to y, right? If we think about this, and this is my I, and this is my j, and then I can dot that with what? R primed. Well, this is a vector valued function anyway, so this is actually going to be r primed of t is going to be dx, because it's a vector valued function. This is going to be dx over dt I plus dy over dt j, and without loss of generality, we could expand this if we had to for vectors or for functions of more variables, right? And then this is going to be dt. So this turns into, you ready? This is the integral from a to b of partial f with respect to x times derivative of x over dt plus the partial of f with respect to y times the derivative of x, or excuse me, of y with respect to t, right? If I dot these two things, this is what I get. And then this is, of course, let's not forget, dt, all right? And then what's this equal? Well, by chain rule, isn't this the derivative of f of r of t? So what I end up with is the integral from a to b of the derivative of f of r of t. Boy, there's a lot of ofs in there, isn't there? Let me see, dt. Well, the antiderivative of the derivative, well, you can see what happens. This just turns into f of r of b minus f of r of a. It's pretty clever, huh? I don't know why I'm getting a little circle thingy, but I'm not too worried. Now, let's try and figure out sort of graphically what this means, because something crazy happens here. Watch. All right, if I have, here's x, here's y, here's z. Okay. So now I'm in 3 space, right? So think about this for just a sec. If all that I need are endpoints, right, then my path doesn't matter as long as I have a conservative vector field. So if I have some point, and I'm going to cheat here. I mean, I should call this some point x. Well, I guess I will. x1, y1, z1, right? And then I have another point somewhere over here, and this is x2, y2, z2, right? And I take a curve that goes, I go from around in space, and I'm going this way, right? I go that way. Or if I take, this is my C, by the way, or I go like that. Doesn't really matter how I do it, right? Because look, as long as the vector field in which I'm playing ball, now these are the curves. This is C, and this guy is C as well. My vector field is going to be in this 3 space, right? As long as my vector field is conservative, it doesn't matter the path from point A to point B. Look at this. This is what the fundamental theorem of line integrals says. It doesn't matter as long as the vector field is conservative. True? Look, this is f of r of b minus f of r of a. Notice it doesn't matter what C is. C is completely almost arbitrary, right? Now, we've got to be careful there. Let's not get too crazy. We'll get into the nitty-gritty details of that here in just a second. Okay, so what this is referred to, there's a word for this, of course. If this is C1 and this is C2, And it doesn't matter the path that, well, careful. Let's be clear. If the integral over C1 of f dr, f dot dr, is equal to the integral C2 of f dot dr. Remember, vector field doesn't change. Path changes, right? And C1 and C2 are piecewise smooth. Remember that? In other words, they're not disjoint. We're not jumping around the vector field to get around. If this is true, then what does that tell us? Well, it tells us that these are independent of path. Again, this is going to be a heavy vocab section, independent of path. So if we've got independence of path, now what does that imply about the line integral? More importantly, what does that imply about the vector field? Well, look, if I've got independence of path by virtue of the fundamental theorem of line integrals, look at what this is. This is a conservative vector field by definition. So we know that if I take the integrals, all integrals of conservative vector fields, and I know you're thinking to yourself, Ripley, what am I going to do with these conservative vector fields? Like, how am I going to determine if they're conservative or not? Well, we'll get to that. Be patient. All integrals of conservative vector fields are independent of path. Which is cool. Independent of path. Okay. Now I need to give you a little bit of additional vocab here. So let me change colors here. Let's talk about a closed curve. Let's talk about, this is kind of a new section, but not really. All this stuff dovetails together. Whoops, a closed, yuck. Let's talk about a closed curve. A closed curve is exactly what you think it would be. And this is going to get a little confusing because we're going to talk about open sets and closed curves. So bear with me for just a sec. A closed curve simply implies that if I start at A and I finish at A, I'm closed. So this is point A, and then here I go. This is some C. And I start and finish at the same point. So I could say that A equals B, right? Really. But you know what? That's a little disingenuous. And here's why. What I'm saying is, if let's say that we're talking about T's, then A and B are not the same thing. They're different. Say A equal, this point right here corresponds to T equals 0, but it also corresponds to, say, T equals 5. I can't say that A and B are equal. They are different. But what I can say is that R of A equals R of B. In other words, I start and finish in the same spot. I have different T values at which that happens. Now, let's try and bundle this whole thing together for just a sec. All right, based on what we know. Excuse me. There's a theorem. There's a couple of theorems that fall out from this idea of closed curves, independence of path, conservative vector fields, and all of that. So bear with me for a sec. Let's give you the first one first. All right, so I've got a line integral of f dr. Remember, this is just shorthand. Keeps it simple. We can call this, if we want to, we can call this f of r of t times r prime of t dt. We can call it f dot t ds. Remember, all of those things are exactly the same thing. It's just that the limits change. So this guy is independent of path, indep of path. And you know how much I love me some if and only ifs, right? If and only if the integral of f dr. Now think about that. What has to happen? What absolutely has to happen? If I start and finish in the same value, or at the same place, excuse me, then the fundamental theorem for line integrals says that r of a minus r of b, or remember this guy turns into f of r of a minus f of r of b, so this guy's got to be 0. I end up in the same spot. So it's got to be 0 for every closed path. Path C in the domain D. Okay? That's pretty useful. So this is true if and only if. So now I've got this relationship between all integrals of conservative vector fields are independent of path. I've got, if it's independent of path, then the integral, if it's closed, right? If I've got a closed path, then it's got to equal 0. And if this is true, then it's independent of path. We've got these logically connected phrases that are really, really useful. Okay, now I've got a little bit more vocab to give to you. So this has to do with openness in D. So we've got closed curves, but we've got openness in D. Let's talk about what that says for a sec. All right, so let's say the D, which really we know, we know, I'm gonna call this D. Okay, we know that D typically refers to the domain, right? Now, but I've got a path. Let's make a path in here. All right, I've got some path C. Okay, first things first. Let's talk about this is going to be C. Okay, I need to define a couple of things first because they're going to be really important. Okay, if D is open, now this is going to get really confusing. What this means, if D is open, this implies. Oh, this is going to be tricky. I'm going to steal this thing right out of the text so that there's no confusion. This means that for every point in D, okay, so pick any point P in D, there exists, excuse me, a disk with center P such that the circle, or the disk lies entirely in D. Now, let me explain what that means. If I pick any point P anywhere, all right, inside of this disk, now inside of D, let's be really clear. The boundary of D is not included, all right? In other words, it's not open on its boundary because I can't create a disk that's entirely inside of D, all right? So pick any point P, and I can open a disk around it that's entirely in D. So as long as I get arbitrarily close to the boundary of D, I can build a little teeny tiny circle. Or out here, I got up here, I can build a great big old circle. So all I got to do, now think about what we've dealt with in the past. Basically, think of these disks as being, well, they're closed intervals around P that are contained entirely with D. But let me make sure that we understand that the boundary of D, if there exists a boundary, then this is not open. The boundary points are not open. It's not that they're closed, it's because that's a different terminology. You can see where this gets a little bit confusing. All right, let's talk about connected. D, so this is 1, and then this is 2. D is connected. And you can probably guess what this means. This is if and only if for any 2 points, for any two points in D, there exists a path between them, a path connecting them. In other words, connecting them. Sorry. In other words, D can't look like this. I've got this and this. All right. In other words, if I've got a point here and a point here, I can't get from here. This should be, for any 2 points, there is a path. This should be in D connecting them. For me to get from this point to this point, I have to leave D, if that makes sense. Okay, so we've got, let's be really careful here. We've got a closed curve and an open D, an open domain. Think of D as your domain. All right, those are different things. Closed curve just really means it makes kind of a loop. Now, it doesn't have to look like a loop, but it makes kind of a loop. Now, with this terminology, we get another theorem. Let me get back to my black pen here. We get another theorem, and this theorem says this. Suppose F is a vector field. I should just call it a VF, shouldn't I? Sorry. A vector field that is continuous on an open. All right, now you ready? Open, connected, D. Okay, so what I've got is, I've got a vector field that's continuous. In other words, I can take partials everywhere, right? I can take derivatives everywhere. Think of it that way, all right? If the line integral of C of f dot dr, again, just shorthand notation, is independent of path, independent of path. I should start calling that IOP. Maybe the next version of the videos. In D. Now, what's that mean? Remember what independence of path means. It means any 2 points, it doesn't matter the path, how I get there, the line integral is going to be the same value, right? Then, this implies f is a conservative, vector field on D. Vector field on D. Isn't that awesome? It's like we tie the thing just in knots, or tied in knots. We tie it in one tidy little bow. I'm tied in knots. You're probably a little tied in knots, but that's okay. Now, what does that mean if I have a conservative vector field? That implies that f equals the gradient of some function f, little f. That's pretty cool. So we've got this conservative vector field, which we've talked about a couple sections ago. We have this wonderful fundamental theorem for line integrals. Then we got a whole bunch of vocab that's involved with it. Now, in this next little section, and this isn't going to take too long, I promise, because this is already a pretty long video, we're going to tie this whole thing in a nice, tidy little bow. There it is again. All right, but I'm going to give you the skills to determine whether or not a vector field is conservative. Okay, that's going to be huge, and it's super easy. It's not difficult at all. That's the coolest part of it. All right, I'm going to give you a little bit more, excuse me, I'm going to give you a little bit more vocab to go along with it, and then we'll be done with the section after I show you how to do one fun little problem that we're going to see a bunch of in this section. Okay, so now we're officially begging the question, how do I know if f, a vector field, is conservative or not? Well, I need a tool, I need a mechanism, because if it's conservative, we know that this equals the gradient of f, right? Well, let's take sort of an arbitrary two-dimensional vector field, okay? Let's call this pi plus qj. Now, if this is conservative, so I'm going to start with if, or suppose, let's keep it simpler than that. Let's start with suppose f is conservative. Suppose f is conservative. All right? Conservative. Well, what do I know? Doesn't this imply that p is equal to the partial of little f, notice little f, big F, with respect to x? Similarly, I know that q is the partial of f with respect to y, right? That's how we build gradients. We take the partials. We stuff the partial with respect to x. We stick it in with I. We take the partial with respect, we stick the partial with respect to y. We stick it in with j, right? Now, I'm going to take a second derivative of these, all right? And we'll see what happens. So if I take, I want to take the derivative of p. But I'm going to take this thing with respect to y. All right? Now, do you agree that if I take the partial of p with respect to y, well, that's just the partial of this guy. That's just the partial of this guy, true? Which gives me the second derivative of f with respect to x and y. If I take the remember, basically what I'm doing is I'm taking the partial over y of this. This is equal to, let's see if I have enough room, d over dy, or delta over dy of df dx, right? Partials. I'm sorry, I'm terrible with that. Now, this is equal to, by Clairaut, this is equal to this, right? I can always switch these guys around. We know that these second partials are with respect to x and y, that we can flip them around. Well, isn't that equal to the partial of q? with respect to x. Now look at that. This is what you refer to as a theorem. The theorem, we just proved a theorem that we get to use now. So suppose f equals pi plus qj. All right, and let's say that this thing is conservative. I should just start shorthanding that. All right, this implies, let's say conservative in D. All right, this implies that the partial of q, partial of q with respect to x is equal to the partial of p with respect to y. If it's conservative, now then this has to be true. Now, is the converse true? Now this one's going to take a little bit more information. And again, I don't want this video to be 9 hours long, but I want to know, what I want to know is, if this is true, does that imply that my vector field is conservative? Because that's really the tool that we need, right? I want to be able to just do this thing and then imply that this thing's conservative. I know that if it's conservative, then this is true. But I need it the other way around to have it be truly useful. Well, the answer to that's a little more complicated. I'll go into the vocab in class, but suffice it to say, 99 times out of 100, it's true, all right? But I'm going to give you the full theorem. It says, let f equal pi plus qj be a vector field. Now notice I'm not assuming that it's conservative, otherwise I'm done, right? On an open, now we know what an open domain is, but I'm going to talk about, suffice it to say that simply connected means simply connected region D. Simply connected means this. If I've got, here's my D. We know it's connected if for any 2 points there's a path that exists between them. However, what if I punched a couple of holes in this? I could still get, if this is D, if I had a point here and I had a point here, I could still get there by a path. In fact, I could get there by uncountably infinite number of paths. But this is not simply connected. This is not simply connected. In other words, we don't want any holes punched in our region, D. Okay, does that make sense? So it can't have any holes. Otherwise, this theorem falls through. If this is true, and P and Q have first order derivatives, partials, first order partials. In other words, if I can take these guys, if they exist, and this is true right here, so these partials of q with respect to x is equal to the partial of p with respect to y, then I know that f is a conservative vector field. Yay! We now have officially conservative VF. Yay! We now officially have a tool to determine whether or not a vector field is conservative or not. As long as D, the domain, the place where we're playing all of our games, is open and simply connected. Now, 9 times out of 10, D is going to be the xy plane. It's going to be r squared. Well, clearly r squared is open and simply connected. There are no holes popped in the Cartesian plane. And any point in the Cartesian plane, you're going to be able to draw a disk that's still in the Cartesian plane. So you kind of get that for free. This looks intimidating. It must be open and simply connected. But it actually works to our advantage really, really nicely because, like I said, 99 times out of 100, D is going to be r squared, or the Cartesian. All right, now is probably my favorite part of this whole section. Because hitherto, all we've had is a bunch of theorems, and this idea of conservative vector fields, and these open domains, and simply connected, blah, 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 blah. Let's put it to work, okay? I'm going to give you something, and we're gonna solve it algebraically because it's going to sort of fly in the face of the theorems that we've already talked about, because I'm going to give us a 3-dimensional vector field F. all right? And I'm going to let this thing be f equals y squared I plus 2xy plus e to the 3z j, okay? These are so much fun. I love these. But they're a little tricky. Now, I'm not going to lie to you. 3y e to the 3z, okay? E to the 3z, okay? Now, we got ourselves a little bit of a problem. This is a three-dimensional vector field, and if you notice, these theorems only work with two-dimensional vector fields, right? So I want to try and prove, I want to try and show that this vector field is conservative, all right? Now, what does it mean to be conservative? Let's make sure we've pounded this into our skulls. If f is conservative, then f is equal to the gradient of some function f, where f is just a function of x, y, and z, all right? This is where f is just a function of x, y, and z, okay? So watch what we're going to do here, because this to me, it makes it all worth it as far as doing some fun mathematics. All right, so let's start with this vector field right here. You ready? What do I know about this coefficient of I? Or in other words, this component of I. I guess coefficient would be the wrong thing because I is just sort of a placeholder in it. Well, I know that the partial of f with respect to x equals y squared if this is a conservative vector field. Remember gradient. We take the partials with respect to x, we stuff it in here. We take the partials with respect to y, we stuff it in here. We take the partials with respect to z, and we stuff it in here. Like, based on what I just said, I know that the partial with respect to y is 2xy plus e to the 3z, and I know that the partial with respect to z is 3y e to the 3z. So far, so good, right? Now I'm going to start with this guy, and then I'm going to reverse engineer all of this, but it's going to take a little bit, so bear with me. Does everybody agree, hopefully, that based on this partial, I know that f of x, y, z, by taking the antiderivative of this term with respect to x, that I will get x, y squared, right? But I'm not just going to get xy squared. I'm going to get some other function, which I'm going to call g, all right? And that function is going to be a function of both y and z. Now, you may be like, whoa, Ripley, what just happened there? Well, think about it this way. If I differentiate f, if I take a partial of f with respect to x, and there's any term over here, right, that doesn't have an x in it, it disappears. So this kind of free of charge gives me gives me y squared when I take the partial with respect to x. But now I have to address this issue, this g of yz. All right. So how do you think that we're going to do that? This is the coolest part. We reverse engineer to get to here, and then we're going to use this piece of information, this partial with respect to y, to deal with this. So if I take this guy with respect to y, well, what do I get? I should put x, y, z there, but I'm going to be lazy. I'm going to get 2xy plus g primed of y, z. Everybody agrees, right? Well, what does that tell me? Look at this. It's beautiful. These two are equal, which implies, so I've got a nice little piece of information here, tells me that g primed of yz is equal to e to the 3z. But I don't want g primed of yz. Think about that. What I want is, I want g of yz. Okay, now this is where it can get just a little bit confusing. So you know what, I probably should I should pay more attention. This is a partial, so I should probably put a partial with respect to y here and here, right? All right, so if this is the partial with respect to y, then what happens here? Well, I can tell that, doesn't this imply that g of yz is going to equal what? Well, there's going to be a y e to the 3z, isn't there? Now, let me write that out. Let me steal this piece of information and stick it in right there so we can look at it. All I did was take the antiderivative of this guy with respect to y. Why with respect to y? Well, because I took a partial with respect to y. So my claim at this point is that f of x, y, z is equal to x, y squared plus y e to the 3z. Now let's look. The derivative of this, the partial with respect to y, will give me a 2xy, plus partial of this with respect to y. Remember, this guy's just a constant. I've got a y in front, pow, and I get that. But you may say, whoa, 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 Ripley, we got to be careful here because there could be an h of z. In other words, there could be a chunk of this function that exclusively has just z's in it, right? Well, if it has just z's in it, when I take the partial with respect to x, gone, right? Now, let's double check. Hitherto, let's make sure that I'm in good shape based on my partials. If I take the partial with respect to x, what do I get? This goes to 0, this goes to 0, and I get a y squared. Yay! If I take a partial with respect to y, I get 2xy. This becomes e to the 3z, and this goes to 0. Yay! But I have to account for the possibility that there's an h of z. How do I do that? Well, it's the same trick I pulled before. Now I'm going to take the partial with respect to z of this guy and see what happens. Well, that term goes to 0. What does this term turn into? It should be relatively obvious. Remember, y is a constant, so I get 3y e to the 3z plus, now I can write h sub z, but since I'm only dealing with one function and that function only has a z in it, right? So I don't want to write the partial of z with respect to z. I can simply write h prime of z. Now look close. The partial with respect to z is this, which equals this. What does this imply? Well, it implies that h prime of z equals 0. If h prime of z equals 0, doesn't that imply that h of z equals some arbitrary constant k? And look at what I have. I've worked my way all the way through all of the partials and picked up all of the pieces of information that I needed. Now I know that f of x, y, z is equal to x squared, x, y squared, sorry about that, x, y squared plus y e to the 3z plus k, which implies what about this vector field? Doesn't that imply that f equals the gradient of little f, which implies f is conservative? You guys are going to love these. They're really fun. They're crazy little logic puzzles. I know this was a long video. I apologize for that, but it's really an important section, and it's gonna give you some cool tools for down the road. We only have a few more sections left anyway, so bear with it, okay? All right. Have a good day. Hope you enjoyed the video. I'll see you.